a class of compounds that will form these particles are alkanes. These are straight chain organic molecules. Sometimes they're cyclo compounds, but this is the class of C12, the C12 alkanes. So we had a major program in this last year to study the chemistry of how molecules like this, and these are typical molecules that would be emitted by in combustion processes and by a number of routes. We had a major program to really understand how, say, if one starts with a molecule like dodecane, C12H26, how does it end up? How do its products end up as these particles? And so we did experiments at different levels of oxides of nitrogen. This is the one sort of chemistry slide, and I'm not going to go through any detail, but the dodecane reacts with OH, forms a free radical, and then under the conditions of the experiment, this radical reacts with another radical, and there's various pathways. And a lot of our work is in detail is devoted to trying to figure out these pathways. And each one of the molecules here that's in a colored box is one that we've identified with a mass spectrometer that sits next to the chamber and and samples the chamber. And the advent of very powerful mass spectrometers has been enormously important in this field, because you have to see what you'd like to see the progression of the chemistry to be able to really understand how it continues to build up in the particle. This is just one data slide from this chemical ionization mass spectrometer showing this progression of chemistry. Here's the first compound. It's formed and then it decays as it reacts to give the second compound in the second chain, and then the third compound, and we can actually see this progression of generations of chemistry that leads to these highly oxygenated products that we then identify with another mass spectrometer in the particle themselves. So it's like trying to close the chemistry, and that's been a very exciting story in the last few years. One of the important characteristics of the organics that are in the particles is the degree to which they're oxidized, simply the number of oxygen atoms carried on these molecules. And one of our students came up with a very clever way of representing this in a diagram where the y-axis here is the degree of oxygenation of the products in particles, and this along here is sort of the kind of hydrocarbon nature. And what she found is that when you look all around the world, most of this is from Mexico City, that as the particles stay in the atmosphere longer, they get more and more oxidized to where after they've been in the air for maybe 2 days, they're all reaching a point of very significant oxidation, and they're starting to look very similar. And this is a process that we're trying to understand. It requires that you'd like to run these experiments for as long as possible, and that's one of the challenges in a reactor where you're sampling and particles are being lost. But this is putting the data in such a way allows you to say, this degree of oxygenation, and I suspect that, and Kirk knows much more about this, of course, than I do, is that the chemical nature of these compounds and something like the extent to which they're oxidized can have implications in human health effects. So now let me switch to Los Angeles, talk a little bit about our own backyard. There was a big experiment that we participated in May 2010. There were our group, and then there were groups from a number of other places, where this was a NOAA-sponsored project, basically to study the air quality in LA at a level of detail that had never been done before in LA. It sort of followed a big study that was done a few years ago in Mexico City. This is a picture from our aircraft. This is out at the eastern end of LA. This is Lake Arrowhead. You can't see it, but this is looking down over sort of San Bernardino. And this is the aircraft that we've used for many years in lots of experiments around the world. It's a Navy Twin Otter. Twin Otter is like a small commuter plane, and it's essentially a flying laboratory. This is the inside of the plane when before a flight. It's a little hard to see everybody, but it's loaded with instruments. Each of the grad students or postdocs are getting their instruments ready before takeoff. This is loading one of the mass spectrometers on the plane. It's the biggest instrument on the plane. And it's the same one that we use in the laboratory, so it gets a nice comparison. So we flew this for a month over LA. The plane was housed in Ontario Airport. And this is a picture of one of the, from one of the flights taken out the window. This is looking toward downtown LA. So this was, it may have been on the same day when the picture was taken by Lake Arrowhead. And we can see this is all these ribbons are the flight paths that we did over a month of experiments. Here's the coastline. The prevailing winds are from west to east. Air blows over, and so here's Ontario right about here, where the plane is housed. We flew almost every day during May of 2010, and we covered the basin pretty much in a similar pathway of going around. We flew over, there was a big ground site at Caltech. We flew over that every day. So USC is right about here, and down over Long Beach and the ships. And then on a number of flights, we went out through the passes and all the way down to the Salton Sea on one flight. And the color here is a measure of the number of very small particles. This is a ratio of ultrafine particles to more regular sized particles. And so the redder the lines are, these are areas where there's a lot of direct emission, very small particles being formed. So one area that we found was over the harbor. So this is Wilmington, Long Beach area. And these are overlaid on that are the flight paths that many of the flight tracks we took over this area. And these are different days, and with different meteorology, some days have higher concentrations than others. But there's certainly a hot spot, as one might expect, over this sort of industrialized area of the basin and where the port is. This is one flight. This was May 28th, 2010. And here are these pie charts let's look at downtown. And it's a little hard to read, but this is the same color scheme. This is organic. This is sulfate and nitrate. The sulfur levels in LA are fairly low. because all the power plants are not burning sulfur-containing fuels. The Long Beach area, this sulfur here is due to the ships in the harbor. Now, this little slice is black carbon, or soot. That turns out to be a very interesting component of particles. I'll talk about in a second. And we can see it's about 4% by mass of the particles in LA. But this one, when we flew right here, this was the 60 freeway, there was a tanker fire. And the aerosol we measured right above that, and I'll show the picture in the next slide, we got almost half of the aerosol was black carbon. And this was it was an unfortunate accident that day. And so it's, that's why I chose to show that. Now another area, this was not during 2010, this was the station fire in 2009, one of the biggest wildfires in California history. Here's Caltech, so it got to within about 6 miles of the campus. And we were doing monitoring on the top of the building. We had all the instruments going. And this is a mass spectrum of the particles. These two peaks, this peak here is this 44. The way the mass spectrometer works is it impacts the molecules with electrons and sort of blasts them apart. But when you get a CO2 fragment, that's indicative of a highly oxidized molecule. And in this triangle diagram that we looked at, this F44, this is the 44, the mass over charge 44. So from the station fire, we saw that the particles being emitted from this big fire were somewhat oxidized, but these are fairly fresh. And it would, one of the interesting things, and this really hasn't been done, is to track the smoke from a fire, for several days. And one would certainly expect to see these particles migrating up toward this vertex of getting more oxidized as they're in the air. But we got some very interesting data on the station fire.